Hello, everyone. So this is joint work with Peter Lammich sitting over there. Yeah, so I don't know if you've seen this formula before. It's called Faulhaber's formula. So if you ever wanted to sum up the 0th power of all the numbers from 0 to n, turns out that's n plus 1. That's fairly boring. If you do the same thing for the first powers, then you get something slightly more interesting, which is commonly referred to as Gauss's formula. So that I think everyone has seen. And it turns out you can do the same thing for higher powers as well. And you always get some polynomial whose degree is 1 bigger than the power that you're summing over. And so the general formula of this, this was studied by Bernoulli, and that's how I found. Actually, it was studied by a bunch of people, Faulhaber as well. I think it was studied by Indian mathematicians as well. So it turns out that, yeah, you can express this polynomial like this, where the polynomials p n plus 1 are defined like this, and the bk in here, these are the Bernoulli numbers. So this is kind of the common denominator of this pattern, and this is what this talk is about. So this was how the Bernoulli numbers were discovered, but they're actually really ubiquitous in mathematics. Like they appear in regular primes, they appear in the Taylor expansion of the tangent function, they appear in combinatorics. So they're really very, very widespread. The Riemann-Zeta function is another big connection. So yeah, they're fairly important in mathematics. And sorry, what's m? M is the power. Oh, that's probably a typo. It should be, I think it should be a k. Sorry about that. Yeah. Okay. So the definition of these things usually is in terms of a formal power series. So you can define the Bernoulli numbers sort of implicitly as they are the sequence of numbers whose exponential generating function is z over e to the z minus 1. And if that doesn't really look like a definition, well, you can also think of it as they're basically the given by the Taylor series expansion of this function, and then you multiply everything with k factorial, and then you've got the Bernoulli numbers. And this also gives you already a recursive algorithm to compute Bernoulli numbers if you want to. It's a very inefficient one, but in principle you can compute them this way. And importantly, they're a sequence of rational numbers. And the numerator and the denominator both get kind of big, so that makes the arithmetic a bit challenging here. So if you just use the naive algorithm to compute them, then you have to do a lot of ugly computations with rational numbers, and that takes a lot of time. So just to give you an impression, these are the first 10 Bernoulli numbers, and you can already see some patterns here that, except for the first one, all the odd-numbered ones seem to be 0. And also, starting with the second one, the signs between the non-zero ones keep changing. And if you continue this a bit further, like B60 already has 42 decimals, and B110 already has 93 decimals. So as you can tell, the numerator grows very, very fast, and the denominator doesn't grows much much slowly. But yeah, these numbers get pretty big. And yeah, some more interesting properties. I already mentioned this, that the odd-numbered ones vanish, and otherwise the signs alternate. And if you exploit the connection to the zeta function, you can also see quite easily that the number of bits in the Bernoulli number itself, if you represent it as a decimal number and you forget about the fractional part, and also the number of bits in the numerator, they're both of the order of k log k. So the denominator is much shorter, but these things grow quite fast, so e to the k log k. And one theorem we're going to need is Voronoi congruence. So this looks a bit complicated. I don't expect you to memorize this. The important thing is if you bring this thing to the right-hand side by dividing over 8 Bernoulli number modulo p as a sum of all the numbers from 1 to p. So the k doesn't really appear here in the sum. So this is, if the p is fairly small compared to k, then this is already much more efficient than computing the Bernoulli numbers in the naive way. But the downside is you only get it modulo p and not the true value. But yeah, so this allows us to compute bk modulo p as a a fairly cheap sum. And of course, you can also do all of this just with integers, integer arithmetic, so you don't need to mess around with rational numbers anymore. And the a in here, if you're wondering about the a, this is basically a parameter that you can choose freely, except that, well, I think there are some side conditions, and the obvious one is you don't want a to the k to be 1, because then this tells you nothing. But yeah, so this is very important. And then this is another one that we're going to use, Kummer's congruence. I think it's actually a consequence of Voronoi congruence. And what this basically allows us is we can, without loss of generality, assume that k is between 2 and p minus 3. Because it isn't, if it isn't, then we can use this. I think this should be a k prime here as well. Anyway, so if it isn't between 2 and p minus 3, then we can just use this congruence here to basically reduce the k modulo p, and then we establish that it has to be between t and p minus 3. So yeah, so that's kind of the two things. And if we combine these two, then this allows us to relatively easily compute bk modulo p. Right, so now how does the algorithm work? There's slow algorithms. This is the obvious one that was used for hundreds of years, which is just you use the recurrence that you get as a side effect of the definition. And as I mentioned, it's very inefficient, so you don't want to do that. There's a bunch of cubic algorithms that you can use. Some of them only use integer arithmetic, which is nice, but this little cubic, which is not so great. The modern algorithms are all quadratic, so they all have roughly the same complexity, which is the one that I showed here. So quadratic plus times some logarithm. One of them that's quite interesting is that so the Bernoulli numbers are fairly closely related to the power series expansion, or the Taylor expansion of the tangent function. So sine function has a very easy Taylor series expansion. The cosine function has a very easy Taylor series expansion. So you can just divide the two, and then you can read off the Bernoulli numbers from the power series expansion. And there's a bunch of tricks how you can do this fairly quickly. So that's one way to do it. There's another one, which is, as I mentioned, the Bernoulli numbers are very closely related to the zeta function. So you can basically just compute the Riemann zeta function using its power series. It converges very quickly. So you can also compute them that way. The downside is that you have to do a lot of high precision arithmetic involving transcendental functions like the exponential function, logarithm, etc. You have to approximate pi to very high accuracy. So you need a lot of this stuff formalized in order to do this. The nice thing about this algorithm is this was the first one that allowed you to compute a Bernoulli number without also computing all the previous Bernoulli numbers. So this was used in the mid-90s to compute, I think, the 1 millionth Bernoulli number or something. And before that, people only went up to, I think, 10,000 or something. But the fastest one is the one by Harvey. So it has the same asymptotic complexity, but in practice, it's much faster, like a factor of 200 or something like that. And the nice thing also that this thing parallelizes extremely well. And it's a multi-modular algorithm. So what does it mean? It means that it works by computing the Bernoulli number that we want, modulo p, for many different primes p independently. So that's why it parallelizes so well. And then you use the Chinese remainder theorem to reconstruct the actual result. And that's something that's very commonly done if you have a problem like that. If you have some complicated thing that you want to compute and the numbers get quite big, or they're rational numbers, then you can basically make your life a bit easier by just working modulo p. And you do that for many primes, and then you can reconstruct the true result using the Chinese remainder theorem. So the high-level algorithm works like this. Our input is the index k, for which we want to compute the Bernoulli number, and we write this as numerator over denominator, and we compute those two numbers as follows. We first sieve a number of primes, and I just say we compute enough primes here, so I'm not going to go into detail, but we can basically make an approximation a priori how many primes we're going to need, and so we just run a prime sieve to get that many primes. Then there's a theorem called the von Staudt-Clausen theorem that allows us to compute the denominator fairly easily. It's just the product of all the primes such that p minus 1 divides k, so that's easy, especially because we already have the prime sieve. Then we compute a more precise algorithm of the logarithm of nk. So basically, we can then compute fairly precisely how many bits the result is going to have, and that's important. And then using that, we get a set of primes such that the product of all of these primes definitely exceeds our numerator. And then we do the important thing, which is compute the result, the numerator modulo p for each of those primes. And then we use the Chinese remainder theorem to reconstruct the nk modulo the product of all the primes. And because we chose the set of primes such that the product exceeds the absolute value of this, by the way, this should be an absolute value here. I forgot that. Yeah, we chose the set of primes so that the absolute value of nk definitely exceeds, is definitely smaller than that. Then we can fairly easily read off nk from that. So we might still have to do some correction in case that the result is negative, but that's still fairly easy to do. So the only really mathematically interesting thing here is the part in red here, computing the numerator modulo p, and I'm going to talk about how we're doing this next. So again, the only part here that's really interesting is the computation of bk modulo p for what I call nice primes. So nice primes are the ones where 2 to the power of k is not congruent 1 modulo p. Why? Because that's basically the part where we can use a faster version of the algorithm. If 2 to the k is congruent 1 modulo p, then we have to use a slower version of the algorithm, but fortunately that happens extremely rarely, so it's basically negligible, the impact on the algorithm. It's not asymptotically slower, it's still the same running time, but the version for the nice primes is about like a factor of 200 faster. That's what Harvey says in his paper. Yeah, so we could in principle also just only use nice primes, but that would make the a priori estimates of how many primes we need much more difficult. And as I said, the effect on the running time is negligible anyway, so we just do it this way, that we use the fast algorithm whenever we can and the slow one if we can't. And we know that the fast one is empirically just the one that runs like 99% of the time anyway. And yeah, so what does an individual computation look like? So if we have a nice prime and we want to compute bk modulo p, so basically the algorithm roughly looks like this. We have an outer for loop that has relatively few iterations. Then we have an inner one that runs very, very often. And the loop body in the inner loop looks something like this. We compute a chunk of digits of the binary expansion of 1 over p, and in every loop iteration we like get to the next 64-bit chunk. And then we cut that 64-bit chunk into 8-bit blocks. And for each of those, we have an entry in our, like we have a table that we maintain, which stores for every combination of I and every possible 8-bit block that we can have, bi. We store some number in there, and we basically add some value that we compute to that table entry. So it's a very, very simple inner loop, very short inner loop. And then once all of that has finished, then we just have to compute some weighted sum of all of our table entries, and then that's the final result. And the important thing here is that this inner loop really has to be as tight and as efficient as possible, just because it runs so very often. So this is the inner loop is really the like all the work basically happens in there. And you might be wondering like why we're doing this thing with these 64-bit chunks. So all of that is optimized such that the table comfortably fits into a level 1 data cache of a typical CPU these days. So of course the formalization abstracts from all of these concrete numbers, so you can easily change the table to a different size if we end up with CPUs with much larger caches. But I think you quickly run into the diminishing returns there anyway, so I think the current setup is actually pretty good already. Because you can't, if you make the blocks larger, of course, then the size of the table grows exponentially. So like going from 8 bits to 16 bits is probably not worth it. Yeah, so, but this is basically the algorithm. And now I'm going to talk a little bit about how we proved it correct. So I'm not really going to explain why it even works on high level. You're going to have to look at the paper if you're interested in that. But I'm more going into what techniques we use to derive it and also to make it efficient. So there's this Isabelle refinement framework and the Isabelle LLVM framework by Peter. And what the way it works is that we start with a very high level view of the algorithm. So we basically start at a fairly abstract mathematical level, which is already algorithmic, but like more like almost pseudocode. So we don't yet talk about concrete data types like 32-bit integers, but we just talk about natural numbers and integers, like God's integers with infinite precision. And we use abstract mathematical notions like, oh, now I want to have the smallest prime factor of the number n, or I want to have the multiplicative order of n in this ring z over pz. And we don't yet talk about how will we actually compute that. And basically, that's how we phrase our algorithm and how we prove that it does the thing that we want to do. And then once we have that, then we start to refine this down to more concrete implementations. So for example, instead of just saying, give me the smallest factor of this integer, we use a concrete for loop to do trial division, or we use a pre-computed prime sieve to do this, to find this thing. And yeah, and then the next step is that we use data refinement, which is where we replace the natural number type and the integer type with concrete things like fixed with machine words. Of course, that means that we also have to add a bunch of extra assumptions because we might have integer overflows. So we have to either make sure that these don't happen, or we have to prove that if they happen, that it's not a problem. And yeah, applications of this framework that were already used in the past is there's this verified Satzur by Matthias Fleury, who's sitting in the audience. There's a collection of verified sorting algorithms, verified all the way down to LLVM, that are comparable in performance to the C++ standard library, which is very impressive. Yeah, so what does it look like concretely? So I picked one example, which is the computation of what we call the factor cache. So the factor cache is just, it's a data structure that gives us, for any integer, it gives us either 0 if the number is prime, or it gives us the smallest non-trivial divisor of the number, which is then, of course, also a prime divisor. And that data structure very easily allows us to check whether a number is a prime number, and it allows us to very easily factor any number in the range, of course, that we support. And on the abstract level, it's really just a function that takes a natural number and it returns either 0 or the least non-trivial divisor. And then the next step is that we prove a concrete implementation of this. So that's a function that takes a parameter, which is basically, this is the highest number that we want to support. That's the highest number that we're interested in. And what it returns is a function from natural number to natural number that implements exactly this smallest divisor function. And this is wrapped in the non-deterministic result monad, which is the monad that you use in the refinement framework, where you phrase all of these algorithms. And then what we can prove is, using the verification condition generator of this framework, we can prove that this concrete implementation, called with some natural number n, satisfies the specification that it gives us some array, well, some function a, such that for all inputs less than n, the function a returns the smallest divisor of k. And then the first actual refinement that we do is that we replace the function type here with a list type. So we no longer return a function, but we return a list of natural numbers. And because the odd indices are kind of boring anyway, right? All odd numbers greater than 1 are, sorry, all even numbers are boring because obviously all even numbers greater than 2 are not prime numbers, and it's obvious what their smallest divisor is. We also save some space by only recording the odd indices in that list. So then we prove that for n at least 3, this more concrete version of the factor cache is in some relation to the original more abstract factor cache. And this relation just captures things like, okay, like we we relate the list that we have now to the original function by just looking at the odd numbered index in the list. And if it's an even numbered index, then we just return 2. So we can have some correspondence there, and that you can show fairly easily. And then the second refinement is this data refinement, where we then replace the natural number type with a word type. So now the end result is and we replace lists with arrays. So the end result is now a function that takes a word of some bit width, w, which is, again, the number of elements we want. And it returns an array. So this is just a pointer and the length of the array in this LLVM monad. And the theorem that we prove is, this is a bit more difficult to read. Like, this is some separation logic stuff that I only half understand. This basically just says that these two things are in some refinement relation where the input is an unsigned natural number implemented by some unsigned word, and the result is some array of natural numbers represented by words and a length word. So yeah. Okay, and so the final correctness result of our algorithm is this. Again, separation logic, a bit tricky to read, but I'm just going to highlight the important stuff, which is that we return a triple of a flag called OK, and numerator and denominator, which are integers, arbitrary precision integers, and the OK flag. If the OK flag is non-zero, then the denominator is the denominator of the Bernoulli number, and the numerator is the numerator of the Bernoulli number. And also we guarantee that if the input k is less than or equal this big number here, then the OK flag will definitely be non-zero. So the reason is why this OK flag exists is that it's very difficult to judge a priori whether we're going to have an integer overflow. And so we basically have a dynamic check of whether we can actually do the computation that the user wants. And if we can, then we return OK equals 1, and otherwise we return an OK equals 0. But we guarantee that at least up until this size of the input, it will actually work. And so what are the challenges? So, well, first of all, there's a lot of components. We needed a prime sieve, and we needed to factor integers. That was easy to do. We needed to do these group theoretic computations, like we needed to find generators in this ring Z over PZ. We needed to compute the multiplicative order in that, so that we also did, and we just used the factorization cache that we had already, because if you know the factorization, then it's easy to do these, relatively easy to do these things. We needed to do very efficient computations modulo P, so for that we used something called the Montgomery form that we also did. Then there's a bunch of floating point computations in the original algorithm, and as you all know, floating point and verification is always a bit tricky. So we replaced it with fixed point computations. And yeah, we needed to compute this binary fraction expansion of 1 over p. And yeah, we also did that. And we needed a fast Chinese remaindering algorithm, for which we use a data structure called remainder trees. And that was also quite challenging to verify in this imperative setting. And arbitrary precision integers we needed because the final result is, of course, some very big integers. So that we didn't do. So there we basically used GMP as a trusted component. And that's possibly future work. But yeah, it's only like in the very, very last step of the algorithm where we actually use this. OK, and I'm going to go over this fairly quickly. So we needed a bunch of maths, of course. In particular, we needed some bounds for this Chebyshev theta function, which is a prime counting function, which is basically like a very concrete version of the prime number theorem, or like a concrete version of a weaker version of the prime number theorem. So that we also had to do. And the whole thing is about 30,000 lines. Most of that is like really just the algorithmic stuff and additions to the LLVM framework. But there are also a lot of mathematical components, but I would say that they're all like fairly general purpose things like Chinese remaindering, yeah, sieving primes, Montgomery multiplication. So all of this is reusable stuff that's kind of general interest, I would say. OK, and I'm going to skip over this. It's quite interesting, but I don't have the time. OK, so the evaluation is that this is basically how much time we take over how much time the original unverified algorithm takes. And as you can see, we are definitely slower than the original algorithm, but it's like it converges to something like a 1.2 factor maybe. So it's about 20-30% slower maybe, which I think is fairly good for an unverified algorithm, for a verified algorithm. And the reason isn't that the verification would have been too hard. It's just that we're not good enough at benchmarking to find out where the problem really is. Like this is, the core loop is so small and it's just a bunch of assembly instructions and we have no idea why ours is slightly slower. But I mean, it could in principle definitely be doable if we knew how to benchmark this. Yeah, and this is the single core performance of our algorithm versus Harvey's. So you see that we have some kind of odd little bumps in here where I'm not quite sure where they come from. But like for large inputs, it kind of converges together anyway. Okay, so conclusion, this is a fairly complex and challenging mathematical algorithm, and we managed to verify it all the way down to efficient LLVM code. And this exposed some things in the LLVM framework that still don't really work, such as, for example, having read-only access to some big data structure shared among parallel threads, which is currently not possible. So this is something that Peter might fix at some point. And yeah, as I said, the performance is not quite the same as the unverified C++ code, but it's pretty close, especially for large inputs, which are the interesting ones. And yeah, and also we are much faster than the mathematical algorithm. So SageMath actually implements Harvey's algorithm. So SageMath is pretty fast, but Mathematica, I think, uses the Zeta algorithm, and that one is much, much slower than ours. So yeah, thanks for the attention. Oh, and I just want to add one thing that for those of you who don't know, computing Bernoulli numbers was actually arguably the very first algorithm ever implemented on a computer. So that was the analytical machine by Charles Babbage, and Ada Lovelace wrote the Bernoulli number algorithm for that one, and was unfortunately never built. But yeah, this was like in the 19th century.